which takes us back to the data link layer. A local area network is for multiple directly connected devices. So in the previous examples, when we studied the data link layer before the midterm, we just looked at two, a point-to-point connection. But now we have multiple. And then because of that, we have need for more complex structures because we have to deal with multiple possible computing devices. And so we use the IEEE 802 LAN model, which is by far the most widely accepted LAN model universally. It's what everybody uses, that's what we'll use. And one of the sub-layers of the 802 LAN model is a logical link control. And we didn't spend much time on that because we said logical link control is the issue of flow control and error control. That's primarily what the logical link control does. And we had already studied flow control and error control previous to that, but now we're bringing that back, right? So you should remember something about flow control and error control. Are there any questions on flow control and error control? Not to move on.
What do we need to know about it for the exam?
What's that?
What do we need to know about it for the exam? Is what they do generally?
Well, what they do generally and what the different, so for example, the one that we focused on for flow control is sliding windows protocol.
Yeah.
And sliding windows protocol deals with the issue of overflow. When the receiver runs out of memory, it has no choice but to throw out packets, even if there's nothing wrong with the packets. So the goal of flow control is to prevent overflows. And the way that you do that with sliding windows protocols, you stop sending ACKs. And when you stop sending ACKs, eventually the link retransmit list on the sender will fill up and the sender will stop sending. Necessarily that implies the sender will also stop accepting data from layer 3. And then when the secondary or the receiver frees up some memory, then the receiver can resume sending ACKs, which will then allow the sender to empty out its link retransmit list, and then it can fill them up again. So if any of that sounds foreign to you, you should go back and study that. Then the error control has to do with managing corrupt data. And there's best effort, which means, well, too bad. You still have to detect data and throw it out. But if you're going to be reliable, then you have things like idle RQ and go back in and selective repeat. And then the other thing we have, which was new, was the media access control. One of the things that's defined at the LAN level is the packet or frame format. And we start with the start of frame and the end of frame, which delimits the boundaries of the frame. And then we have a sequence number, if we're going to be reliable. And then we have the MAC source and destination address, which in the case of Ethernet and Wi-Fi is a 6-byte entity for source and destination. And that's where the MAC, so the MAC, we have the MAC address, and we have contention resolution. So with multiple possible devices, the media access control uses one of several algorithms to determine who gets to talk next. Also within the LAN, we have the issue of topology. Which is the means of physically interconnecting the multiple devices. And so we have a star, which sometimes today is called a switch. Switch is an implementation of a star, like a gigabit Ethernet switch. We have a ring and a bus. And those are the topologies. And then going with those are the MAC protocols. And there's different types of MAC protocols for each one of those topologies. So we have priority-based, fairness-based, and random.
Does that last one say bus?
Yes,
Topology?
ring, star, and bus. If there are any questions, stop me, because I'm not going into details on everything. Like for example, if you don't know what a priority-based MAC protocol is versus a fairness-based versus a random-based, you can ask me. Today I'll answer, Friday I won't. I'll just look at you like, oh. If you don't know what a ring, star, or bus topology is, you can ask me. Everybody good with all that?
Can you go over the differences?
Which, for topology or for MAC?
For the
protocol?
MAC base, for the priority,
So,
fairness, and random.
with the priority based, before every packet is sent, there's an arbitration cycle necessarily to determine who's the highest priority. Then once the highest priority is determined, that is the next packet to go. And so for what that allows you to do is emphasize high priority data will always go first, with possibly starvation for low priority. If you have way too many high priorities, you might end up with the low priorities never being sent. Frankly, that's an issue of capacity. You know, you should be able to, and I won't get this deep into it, but if you have starvation, that's like rush hour and I-75. You've overloaded your network. You need to tell the user, either get a bigger network or tell the users to cut it out. That's a design issue. The fairness base typically use like a timer or an ordered assignment. So one way is everyone gets a time slot, and you transmit during your time slot. So you get to transmit at 2 o'clock, you transmit at 3 o'clock, you transmit at 4 o'clock, and you voluntarily surrender the network when it's not your time slot, and when it's your time slot, everybody else voluntarily surrenders, and that requires the provision of global time. So the cellular system works on that. So the cell tower provides global time, and the cell users synchronize to that global time. They're assigned time slots. Yes?
Is it a round robin?
Well, that's another form of it, but round robin doesn't explicitly assign a time slot. Round robin, you just go around. You get a turn, you get a turn, you get a turn, and typically it's like one packet. You can send a packet, you can send a packet, you can send a packet, and I can send a packet. And we just go around. Timing is a little bit different. You get a slot, so you get your slot, and you can either send nothing or you can send everything up until your slot ends. So it could be multiple packets that you could send, but when your time slot ends, you voluntarily surrender. They're related. Those are fairness-based, but they're different. And then random is just random. So with random, you always have CSMA. CSMA is carrier sense multiple access. What that means is before you transmit, you listen. If somebody else is transmitting, you wait. And then when you listen and nobody's transmitting, then you get to transmit. And Wi-Fi uses that. But Wi-Fi uses CSMA, CA. You need me to write this stuff down, or because we're going to have to erase stuff. So CSMACA is carrier sense multiple access with collision avoidance. What that means is before you send your 1500 byte or 1000 byte Wi-Fi packet, you send a couple of very small packets. You send out a request to send, and when you send out a request to send, anyone who hears that knows that you're trying to send and they don't send. That means you got there first. So if you were getting ready to send out a request to send an RTS, but I sent one out first, then you have to stop. If you hear my RTS before you get your RTS out, then you have to wait. So it's random in that sense. And after the RTS, then the wireless access point will send out a clear to send, a CTS. And the reason they do that, the reason that's important is, I guess I have to, so here's your wireless access point, here's you send out an RTS, here's the coverage area of the access point. Well, maybe this person over here didn't hear your RTS and they don't know that they have to stop. But when the CTS goes out, the clear to send, then that person will hear the clear to send. So there's a handshake, a request to send, and a clear to send. Those are small packets. And then after that time, there's a block time for your frame. You get to send your packet without interruption and without collisions. The problem with random is the probability of a collision. That if I start to send data, and you send data, the signals will superimpose and we'll get nothing. Collisions normally occur when somebody is transmitting and everybody's waiting. So I am transmitting and 4 or 5 of you want to transmit. You hear me transmitting and you wait. And as soon as I'm done transmitting, the 4 or 5 of you attempt to transmit and then you have a collision. The RTS-CTS reduces the probability of that by, not quite a factor of 10. But by sending a very small packet, it's unlikely that that will collide. But by sending a very small packet like the RTS, that reserves the time for me. So it's an agreement. If you hear the RTS, then you'll wait your turn. So it's called reducing the collision domain. So the collision avoidance, so it's CSMACA, carrier sets multiple access with collision avoidance. The collision avoidance part is the RTS and CTS. You send out 2 very small packets, and when that's done, everybody else within the coverage area of the wireless access point knows that they're going to wait the entire time for you to send a large packet, up to 2,000 bytes. So by sending 3 or 4 bytes, you reserve the slot for 1,000 bytes or so. So that's random access. So we talked a little bit about random, a little bit about fairness, and the common priority based is CAN. CAN is interesting in that it is different. The rule in CAN is that you do your CSMACA, and what can happen is multiple nodes can transmit at the same time. But the bus line uses a wired OR logic, actually media access control, not the bus line. The media access control uses a wired OR logic, so the normal state of the bus line at the link layer is high. And if you're transmitting a 1, you leave the bus high for 1 bit time. So if you're transmitting at a megabit per second, you leave the bus high for 1 microsecond, and that effectively transmits a 1. If you're transmitting a 0, then you pull the bus line low for 1 microsecond. And so the CAN, the arbitration occurs over the first 29 bits of the CAN packet. The CAN packet is up to 128 bits long. 64 of those bits are data. You can have up to 0 to 64 bits of data. Bits, not bytes. And the other 64 bits are overhead. There's a CRC field, there's a start of frame, there's a 29-bit identifier. And this 29-bit identifier is where you can actually have effectively collisions, but the thing with CAN is that if this is my CAN bus, CAN stipulates that when this node sends a bit, everybody has to be receiving that bit while that bit is still being sent. That creates a relationship between the maximum length of the bus and the bit rate. So if we assume roughly the speed of light at a megabit per second, that's 1 microsecond per bit, a bit is somewhere between 200 and 300 meters long, depending on, if it's exactly speed of light, it's 300 meters. If it's a little less than copper, the signal speed is a little less than the speed of light, but say 200 meters. So that implies the length of the bit transmission is going to be, let's say, 200 meters. And then the maximum length of the CAN bus for 1 megabit per second is defined by the standard as 40 meters. So therefore you have a bit transmission time of 1 microsecond, which equates to 200 to 300 meters. And everybody will be receiving that bit while you're still sending it, because the maximum separation between any two nodes is 40 meters. And so what happens when you're sending the identifier, if you're sending a 1, you leave the bus high. If you're sending a 0, you pull the bus low. If while you're sending a 1, you see the bus line go low, then you drop out. Meaning a dominant or a 0 bit takes precedence over a 1 bit. And so if you think about that, if I have several nodes, let's just take 2 identifiers. Let's say this is their identifiers. Then over these first 3 bits, they're just going to monitor the bus line. On this 4th bit, the node sending this packet will pull the bus line low. Then the node that's observing, because it's sending a 1, will drop out. And so if the 29-bit identifier is unique, and it has to be unique, well, you have 2 of the 29 choices, so that's quite a few choices. Then at the end of the 29-bit identifier, everybody will have dropped out but 1. And that 1 that has not dropped out is the one that's allowed to transmit. So CAN actually allows collisions over the first 29 bits, but because of the strategy of CAN using a dominant bit, is when you pull the bus line low, and a recessive bit is when you leave the bus line high. And the rule that if I see the bus line go down when I'm monitoring, then I drop out. And the biggest factor is the restriction on bit rate and bus length. This only works if everybody's receiving the same bit at the same time. And so with CAN, it's really, you're not going to get faster than 1 megabit per second at 40 meters. If you want to go faster, then you have to shrink the bus. So if you want 10 megabits per second, then maybe your bus is only 4 meters long, and that's not very practical. So the 3 networks that you should have some familiarity with is Wi-Fi, which is IEEE 802.11x, right? There's 30 versions of Wi-Fi, but they all have in common the 802.11. And then what follows 11 depends on what variation of Wi-Fi you're using. Then Ethernet is IEEE 802.3, and then CAN is not an IEEE standard; it's an ISO standard. And so you should have some familiarity with CAN, Ethernet, and Wi-Fi. Along the lines of maximum packet size, MAC address, media access control. And then, so we said Wi-Fi is random access, CSMACA, CAN is priority based. Ethernet is neither, because in Ethernet you don't have a shared medium. In Ethernet you have a switch, and everybody has their own dedicated connection into the switch. And since it's not a shared connection, you cannot have a collision. But what you can do with an Ethernet switch is overload it. if this is, we'll say this is a 1 gigabit per second switch, which normally those have, you know, I've seen 16, 24 port switches. The aggregate throughput of that switch cannot exceed 1 gigabit per second. A lot of people don't realize that because each of these is a 1 gigabit per second line, and people assume, well, I have 24 ports that each support 1 gigabit per second, therefore I can send 24 gigabits per second. That is not true. The entire switch, if you don't want it to overload, has a throughput of 1 gigabit per second. If these are each sending you 1 gigabit per second to this port, then you're going to overload this link, and what's going to happen is packets are going to drop. Because that one link can support 1 gigabit per second, but if you have two devices sending to it at 1 gigabit per second, it's going to start overloading. It can only support 1 gigabit per second. So if you never want to overload, then keep your aggregate throughput below 1 gigabit per second, or whatever the switch bit rate is, 100 megabits per second, 10 megabits per second. Whatever that switch bit rate is, that's for the aggregate of the switch. If you don't want to drop packets, you're guaranteed that if you stay below that, you will not drop packets from overloading. You're taking your chances if you go above that. You might, but you're not losing packets to collisions, you're losing packets because at each one of these ports is a buffer to hold packets. And when that buffer fills up, then any packets coming in will be thrown out. So that's an overload, it's not a collision. All right.
You said both Wi-Fi and Ethernet were both IEEE 802?
No, Ethernet is IEEE 802.3.
Okay.
Wi-Fi, there's a bunch of IEEE 802 standards out there defining specific protocols.
Okay.
802.3 is Ethernet, 802.4 is FDDI, which we didn't talk about, 802.5 is IEEE token ring, which we didn't talk about. There's a bunch of them. 802.11 knows Wi-Fi, 802.15, Bluetooth falls under that. But the only ones that I care about that you guys know is 802.3, which is Ethernet, and 802.11, which is Wi-Fi. But the reason I bring up 802 is that is the de facto standard for LANs. De facto means it's by way of fact. There's lots and lots of standards out there, most of them nobody even cares about. There's lots and lots of standards committees. But the ones that people use every day are the de facto standards. CAN is the embedded systems de facto local area network. It's in billions of embedded systems, including cars and trucks and airplanes. Ethernet is the de facto LAN cabled medium local area network. It's what's predominantly used like in the network in this campus, going router to router. Wi-Fi is, I guess you could call it a de facto standard for the last part of the network. Now we're transitioning a little bit into autonomous systems, but if you have all these routers, we'll use circles for routers, you tend to cable routers together because the cable is way more reliable. It supports a much higher data rate. Regardless of, when the Comcast person tells you, oh, we have 500 megabits per second of Wi-Fi, like whatever, dude. That's marketing. I don't know where they come up with that number from, but it's exaggerated. The cable link is going to be far more reliable because you're not going to drop packets. And because routers don't move, the benefit of wireless, it lets you move around. And routers tend not to move, so they connect them with an Ethernet cable. And then at the edge of the network where you have your subnet router, your Wi-Fi is for connecting your subnet router to what we call edge devices. Your devices, they're at the very edge of the network. So you have Wi-Fi in a sense is standardized for this part of the edge network, and it's a de facto standard. It's the most widely used. You know, Bluetooth is used a little bit, but it's mostly Wi-Fi that's used for connecting into the network. But it's important to know it's only at the edge of the network. It's only for the user devices. So user devices are devices that generate and consume data. Network devices are devices that move data. Our focus is on the network devices because of the name of the class. Then when I say the edge of the network, I'm talking about the user devices. So the user devices are the devices that need the network. They want data moved on their behalf, but they don't move data. And they're the ones at the edge of the network. And here, to provide the convenience of moving around, it's wireless. So that's about it for LANs. So I didn't write everything on the board, but we've talked about everything that I'm concerned about that is fair game for the exam. Are there any questions on any of that? Good with LANs? Okay. So the exam will be the same format. We'll have a few multiple choice and a few matching, kind of I always thought it made the exam easier, and historically students have asked for that. And then we'll have, probably be a 70-30 split. 70% of the exam will be problems where you have to solve something. I would say be careful though, there are a few students who lost a ton of points on like the multiple choice and matching, so don't get stressed out. Take your time and read thoroughly. I try not to be tricky about it. And the matching, the multiple choice and matching will be along the lines of quiz questions. They won't be very deep. But again, be careful because there was at least one student who would have gotten an A on the problem solving part of the exam, which is, I think, the harder part, but they just got careless, I think. It's like, how could you, I think someone got all the matching wrong. That's hard to do. The way you do matching, you start out with the ones you know for sure, right? Like you don't just answer the first one, and if you don't know it, guess. You look at all the matching possibilities, the ones you know 100%, you eliminate those, right? Then if you have to guess on a couple, but if you get one or two of the first ones wrong on matching, that can cascade and get the whole thing wrong. All right, so the next thing is internetworking, and the focal point of internetworking is the autonomous system, right? So this is defined as a privately owned network. This is like the core piece of the internet. And so these are like, we use U of M Dearborn as our example, but it applies to your networks at home, which, if you're a subscriber to Comcast or AT&T or whatever, then they are your service provider. It applies to U of M Dearborn or Ford Motor Company type network, which tend to be Class B networks. Your home networks tend to be Class C networks. Your U of M Dearborn type networks tend to be Class B networks. And then the federal government has very, very large nationwide networks that are Class A networks. But irregardless, those organizations by privately owned, I don't mean that individuals own them, but the organization owns them. And the organization has to purchase routers, they have to purchase switches, they have to purchase cables, and they have to hire a staff, which is the IT staff, and then they have to set it up. They have to decide where the routers go, where the switches go, they have to run the cable, and then they're responsible for maintaining it and upgrading it. And that's an autonomous system. And the autonomous system then consists of interior routers and usually one exterior router. And the exterior router is at the boundary of the autonomous system and routes outside of the autonomous system and routes traffic. It's in and out, it's bidirectional. And to what? To other autonomous systems. So we call this the core network, and all the other autonomous systems interconnect to each other through the core network. And that's exterior routing. And the protocol that's most widely used in exterior routing is BGP, or Border Gateway Protocol. And then we have interior routing. And interior routing is within your autonomous systems. And we kind of use U of M Dearborn as our example. And we said, well, maybe every building has its own interior router. You know, I don't know if that's true or not. And then we said the other type of a subcategory is a subnet router, or otherwise known as a gateway router. And these are interior routers that are special in the sense in that they connect to host devices. So we'll show the host devices as squares. And if your Wi-Fi, you know, so the solid lines are Ethernet, and if your Wi-Fi will show us a dotted line, and the host devices are the squares, and then that would make these subnet routers or gateway routers. The terms are interchangeable, and that these are the routers that directly connect to the host devices that are the users. And that not all interior routers are subnet routers. Some interior routers route within. Typically, what I would say the setup in a building like this would be is you might have one interior router for the building, and then for different floors or different wings of the buildings, you have subnet routers, and then the subnet routers feed into the interior router, and then you route between buildings using the interior routers, and then you route between floors or sections of the building using subnet routers. Something like that, right? That's totally up to the IT staff to figure that out, right? They study it, and then they survey it, and they analyze it, and they come up with their, yes?
So at the top there is a device, and then all those other stuff,
Oh,
are those
sorry.
routers?
Yeah. I drew this as a boundary. So this is the exterior router.
Okay.
These are interior routers.
And those interior routers, are they subnet routers, or they're
No,
just
not all.
okay?
So a subnet router is a subcategory of an interior router
Okay.
that connects to host devices. Not all interior routers connect to host devices.
And that one you have down there is the gateway router, the
Well,
bottom right?
gateway and subnet router are interchangeable terms.
Okay.
They're two words for the same thing. They're special in that they are interior routers that connect to host devices.
Okay.
And then that connection is typically Wi-Fi, or in some cases, if you have a desktop, it's Ethernet. Ethernet is faster than Wi-Fi. It's more stable. But you don't get to walk around. So a lot of especially like in engineering labs where you have these high performance desktops that are doing specialized engineering applications, those are Ethernet. Because the desktops are bigger CPUs, they can generate, they're faster than your laptops. They have more RAM than your laptops, faster processors. So Ethernet is still used, but for your, I guess what I'd call your everyday user, Wi-Fi is pretty popular. If you're gonna go to Starbucks and, buy stuff off Amazon. So for the IT systems, CAN is for embedded systems, right? So we differentiate between embedded systems and information systems. Information systems, so someone defined information as data that is interpreted by human beings. So it's all data. Embedded systems move data, information systems move data, but the difference is the type of data. In an information system, the human is the end user. And human beings like lots and lots of data. So human beings like to look at pictures, and pictures, you know, one high-def image is 50 million bits. One sensor signal is like 16 bits. So one of the differences is in the size of the data. Embedded systems is like CAN, right? You have your engine control ECU reading different sensors on your engine and controlling your fuel. And the difference there is there's no human being interpreting data. So it's not information, it's just data. It's sensor data, it's fuel injector data. And so the embedded systems, there's no human being there. And the data just tends to be a lot smaller. You know, it's just the nature of the beast. Where most of what the world, well, I won't say most anymore. I'll tell you, the embedded systems communications is evolving in its own world, but it's evolving quickly. I would say you're finding things like CAN in more and more devices. And so, I don't know which is a bigger world. It used to be the information systems, but embedded systems is a big area now. I mean, especially robotics and autonomy. There are lots and lots of embedded networks out there. They're just not everyday visible like Amazon, right? So many people, so your information networks are human users, and the dominant data link layers there are Ethernet and Wi-Fi. And then for your embedded networks, CAN is pretty much dominant. Not that there aren't others out there. There's a host of other embedded network protocols out there, but CAN is the one that I would say is by far the most widely used. And in many countries, you're legally obligated to use CAN in cars. It's for maintenance reasons. Okay, so yeah, so what do we need to know about this thing? Well, keep in mind there's always a data link layer here. So we're showing kind of your typical layer 3 view. We're showing routers connected together, but there's always a physical layer, there's always a data link layer, don't forget that. The dominant data link layers used in autonomous systems is 802.3 and 802.11. 802.11 primarily on the edge, and 802.3 the interconnect routers, but also for higher end users who want higher data rates. It's privately owned. We have subnet routers, and we have exterior routers and interior routers. And so I think that's all we have on what I'll call the structure of an autonomous system. Any questions on the structure of an autonomous system? And then we talk specifically about the IP protocol, the IP, capital I, capital P.
Are we going into the interior router protocols?
Oh, we haven't got there yet, so that's a different set of notes. So we're still talking about autonomous systems. And the most widely used layer 3 protocol is the internet protocol. Layer 3 is called the network layer, where there are network protocols. And there are many, many network protocols, like there are many, many data link layer protocols, but there are only a few people care about. And the IP is the most widely used internet protocol. There's IPv4 and IPv6. The major difference is 32-bit versus 128-bit address. And the reason IP version 6 was pushed out as a separate protocol was the concern that with a 32-bit address, we could only support 4 billion some odd users, and that we would run out of IP addresses. Hence, they came up with IP version 6 that offered a much larger address space that you would never run out of users. So we think today, who knows? IP version 4, though, extended its life by the concept of address reuse. So IP version 4, someone said we're going to have private IP address, we're going to have public IP address, and private IP addresses you can reuse. So now you can support many, many, many more users, and there's no reason to get rid of IP version 4. IP version 6 had better security support, had better multicast support, but along the way, IP version 4 picked up improvements as well. So both protocols have evolved. Both protocols are widely used. For the IP address, we focused on IP version 4. Because 32 bits is easier to work with than 128 bits. The same concepts of addressing apply to IP version 6, but we discussed those in the context of IP version 4. And so we have class A, B, and C networks. And the class of the network is, we have 4 octets that are 4 distinct values. And you can represent them as hex or decimal. Naturally, they're binary. And the class of the IP address is determined by the position of the first 0 bit. And the class A network has a 0 in the first position, and that's how you know it's a class A network. By having a 0 in this position, you necessarily regulate the remaining 7 bits. First bit has to be 0, so you have 7 bits to play with, and the values of the first byte of a class A network can range from 0 to 127. So if you see an 86 in the first octet, you see a 93, you see a 24. If you see anything that's between 0 and 127, that's telling you that's a class A network. A class B network has a 0 in the second position. And that's how you know it's a class B network. That necessarily, if you say, well, this can be whatever I want, that would be 6 bits. So you have 2 to the 6 different possible values, and that ranges from 128 to 191. So if the first byte is any value between 128 and 191, then you know that it's a class B network, because you can only have, there's only 64 possible values you can have there, because the first 2 bits are predefined. And then we have a class C network. In the class C network, we have the 0 is in the 3rd bit position, which fixes the first 3 bits. So now you have 2 to the 5th, or 32 possible values, and that is 192 to, what is 192 plus 32? It's normally 190 plus 30 is 220, so 224. I think that's right. So if the address range is between 192 and 224, then you know it's a class C network. And then we have the size, so now we know how to identify them, right? So in a class A network, we have a 7-bit network ID. I'm going to write it this way.
You said it was 192 to what?
192 plus 32 is 224, right? Check my math. And I guess what I'm getting at is you can derive these, right? If you know where the first position, the determining factor is where's the first 0. If you know where the first 0 has to be, then what precedes it must be a 1. And then you can actually derive the range if you think about it. I mean, I gave you the ranges, but I was also pointing out you could derive it, right? Because what I was saying is, like, for example, for class C, I've predefined the first 3 bits has to be 1, 1, 0, right? That leaves me with 5 bits. That means I have 32 possible values, right? Because 2 to the 5 is 32. So if it starts at 192, then 192 plus 32 should be 224.
Yeah.
But probably most of you just write this down on your cheat sheet. So the network ID and the host ID. So this is governed by the Internet Engineering Task Force. Is a very large organization that regulates the internet. And they tell you what you cannot and can't do. And the IETF assigns you your network ID. If you want to have a network, you have to apply to the IETF. And if your application is accepted, then they will assign you a network ID. In particular, the subgroup is the IANA. So the IANA is the group under the IETF that regulates IP address assignment. And if you have a Class A network, you have a 7-bit network ID and a 24-bit host ID. And those are large networks, and there's only 127 of them out there. If you have a Class B network, you have a 14-bit network ID, and we'll say this is prefaced by a 0, this is prefaced by a 1, 0. Is that confusing? Maybe I should do this. Just make a note. That's by a 0, that's a 1, 0. And you have a 16-bit host identifier, and if you're Class C, it's 1, 1, 0. And you have a 21-bit network identifier and an 8-bit host identifier. Does that add up? Yeah, that adds up. So you have 32 bits to work with. The network definition class identifier takes up the first couple of bits. What's left is your network ID, and this is the network. This is what identifies your autonomous system. So I would liken that to Dearborn, Michigan. Right? That identifies a whole bunch of computers that will have the same network ID. So every computer U of M Dearborn, I think what was it, 141.215? That's the U of M Dearborn network ID. That means every host computer within U of M Dearborn has to have an IP address with those same 2 network ID. And then the host ID, so this is governed by the IANA. This is controlled by the IT staff. It's up to the IT staff to assign the host IP addresses. And they can assign them however they wish. You can see that as the size of the network shrinks, the number of networks available grows. So I have a couple of million Class C networks. You have, what is 2 to the 14th, I forget. 16,000? No, bigger than that. I don't know. Whatever 2 to the 14th is, I can't remember off the top of my head. I think, anybody know what it is? It's a lot. It might be 16K. Is 2 to the 14th 16K? Yeah, I think so. Anyways, and then the number of hosts. Some of these are reserved.
Yeah, 16,384.
Okay, so 16K. So and you guys, computer engineers know, you should know, when we say 16K, we mean 2 to the 16th. That's sometimes, not always. When you're talking about things like memory, if you have 8 gig of RAM, well, you have 2 to the whatever, right? It's not 8 gig, it's not exactly 8 gig. All right.
Does that say IETF?
IETF, Internet Engineering Task Force. I forget what IANA stands for, Internet Address something or other. But IANA regulates IP addresses. IANA assigns the network IDs. You don't get to pick your own network ID. You apply to get a network identifier. And then once you get your network identifier, you can set up the host field however you see fit. So any questions on that? Let's see. So, what is option? So this is what the IANA says you can do. And you don't get to change your network ID, but you can do whatever you want with your host ID. And if you look at your autonomous system, here's your exterior router, here's your autonomous system, and I guess we'll say just purely interior routers, we'll give them an I. And then subnet routers, we'll mark them with a, you know, these are interior routers. That subdivide, and then the subnet routers are what interconnects host devices. And this is where we come up with the concept of subnet. So if this is my network ID, let's say it's 141.215.0.0. The zeros are reserved for the identifiers. Ones by default are reserved for routers. The 0 is by fact reserved for the gateways. And then all ones are FF or 255 is for broadcast. So some of the, you have the assignment of these last 2 bytes are up to the IT staff, but there's some convention about some are reserved. And so if this is my network and I didn't use subnets, then when a packet came in here and it would have whatever 2 bytes there, I would have to send it throughout my network in order to find the host. It would have to go here and here and here and here and here and here, because that's the way it would work, right? I know my host ID, so my host ID is somewhere, but I don't know where, so I'll just send it to everybody and somebody will find it. And that's ineffective, right? That's not a good way to do things. So we create the concept of subnet, and when we talk about IP address problems in context of subnet routing, we'll use like the U of M Dearborn example, the Class B network, right? And so if we're using a Class B network, then we have our net ID, which is fixed. And since this is 141 and it falls between 128 and 191, we know right away it's a Class B network, right? And when we know that it's a Class B network, we know that these 2 bytes are the network ID, and these 2 bytes are the host. And in U of M Dearborn, they divide the subnet as 8 bits, and the host, so you have a subnet ID, and then a host, and that particular division is up to U of M, or whoever owns the autonomous system, they can decide that. So you can say, I want 12-bit subnet with 4 devices each, which would give you a lot of subnets with few devices. Or you can say, I want a 4-bit subnet with 16-bit host IDs, and that would give you a few very large subnets. The beauty of 8 and 8 is we don't have to convert it to binary. You know, if we said that we have a 4 and 12, then we'd have to convert this to binary in order to analyze it, and that's not fun. So we said we use the same thing U of M Dearborn does. We would use 8 and 8, and that way you can just look at the octets. And this one identifies the subnet. So when we identify the subnet and a packet comes in here, what can happen is, here's this subnet, then you know you just have to send the packet to this subnet. And you don't have to involve the whole rest of the network. And so that's a ginormous savings on the number of packets you need to generate. And any savings, any packet you don't use, any packets that you don't have to send results in capacity in your network that you're not using. So effectively, by using subnets, the one way to look at it is I have a lot of, I'm using my network capacity much more effectively. Every network has a finite capacity. And the finite capacity is the point at which you start losing packets because you've overloaded the network. You know, I-75 at rush hour is an example of an overloaded freeway where traffic slows to a crawl. Well, you can do the same thing with your network. You can overload it to such a point that your packet flow slows to a crawl. And by reducing the number of packets you have to send by an order of magnitude, you've essentially freed up a lot of capacity that would otherwise have been used. And so this is why we do subnetting. And the reason we know in U of M Dearborn that it's a 8-bit subnet is because the subnet mask is 255.255.255.0. And we know the network, that has to be the network mask, right? So the mask is used, you add with the mask to get rid of the part of the IP address you're not interested in. So when you're routing between autonomous systems, all you care about is the network ID. For packets destined for U of M Dearborn and you're at Ford Motor Company and you're a router, then all you care about is getting that router to the U of M Dearborn exterior router. So all you want to look at is the network ID. Hence, you would have 255.255, or I guess I'm lazy, I like FF. So your network mask for Class B network is FFFF00. And then when you add that with the IP address, the subnet and host ID fields drop out and you just have the network ID field. And then we did that IP config and we saw that the subnet mask was this. And that's why we know that it's an 8-bit subnet, because that's the part that's all ones. And then once you get into the U of M Dearborn system, then you add this with the IP address, and this is the only part you care about. And it might be useful to bring it up again. We've looked at it a few times. It's easy to do.
Without the subnet, the entire 16 bits is originally the host ID, and then it just gets split up, right?
Well, it has to go everywhere to find the subnet router. Well, you don't have a subnet router. You have the concept that you would have routers connected to host devices, but we wouldn't, I guess you'd call them gateways. But if you don't have subnets, then you don't have subnet routers. And you would have to send it to every router because you don't know where the host is.
So if you don't have that subnet and...
Well, think about if in Dearborn, Michigan, all we had was house numbers without streets. You just had a bunch of numbers from 1 to, see, there's 100,000 residents. So you have, say there's 10,000 houses. So you have numbers 1 through 10,000, but there's no streets, they're just arranged. And you would have to go to every house and see if it's 10,000, right? Because you don't have streets. Now, if you have streets, then you look at the street and you say, well, you need to go to Maple Street, and then you go to the street number. And then you know all the other blocks in Dearborn you'd have to look at, right?
Yeah.
So that's the concept of subnet. It's like if I were used to the mailing address, then Dearborn, Michigan would be the network ID, the street would be the subnet ID, and then the house number would be the host ID. And if you don't want subnets, then just imagine you have Dearborn, Michigan with a bunch of house numbers. And you have to find the house. And you know, with the street, you can narrow it down to the street. You eliminate 90% of Dearborn. You don't have to look at, right? You have to look at one street. Well, with the subnet, you eliminate 90% of the network you don't have to look in. You're just looking for that one subnet. Does that make sense?
Yeah.
So that's the class 6 IP address. It's 128 bits, and I don't really want to look at it. It's a lot. Oh, okay. Uh-oh. Well, this is going to take, we'll look at it when it comes. We'll keep going and we'll come back to it. You got to cycle power to turn this thing on. So if whoever leaves doesn't turn it off, it goes into some kind of sleep mode and won't turn on. And then if you come next, you got to turn it on and off. So let's see, what else can we say? Yeah, so that's the concept of subnets, and when this thing fully shuts down, we'll bring it back up and we'll show you how U of M Dearborn is set up. And then that's how the routing would work. So the network ID gets you to the autonomous system. The subnet ID gets you to the subnet. The host ID gets you to the host within the subnet. And collectively, we have the IP address. The IP address is unique for every device in the world. Just like your mailing address better be unique. If someone had the exact same mailing address as you, that'd be a problem, right? Because where you send the package to. So I think the IP address, that's a good analogy, is using the mailing address. And the routing kind of works the same way. I mean, if you think of how they send a package, if they're sending you a package from Taiwan, they don't care about your street number in Taiwan, right? They just want to get it to somewhere in the United States. And it's the same way with, when someone's sending you a packet from outside of you in Dearborn, they just want to get it to the Dearborn exterior router. So all they're worried about is the network ID. Then the next level is all you're worried about is the subnet ID. And when you get to the subnet router knows where you are and will get you the packet. So keep in mind the reserve fields. So primarily the zero. So a network ID is not an IP address. So that's a good multiple choice question. Network ID is an identifier, right? Network identifier. Subnet identifier is not an IP address. The IP address is an IP address. The IP address consists of three components: a network ID, a subnet ID, and a host ID. And those three things together give you an IP address. All right, so there's you over in Dearborn. And so this is this computer's IP address. It's in the 128 subnet with 206. Why do I know this is a subnet? Because of the 255. I know because of this 141, I know it's a class, and the reason if I say something about 18 times, then probably you should understand it. So I know, how do I know this is a class B network? Because the 141. That tells me this is a class B network. Then what do I know the network ID is? The network ID is 141.215. And then what is the network mask? The network mask is going to be FF. How do I know it's an 8-bit subnet? Well, this last FF, because it says subnet mask, right? So that's this last FF, because I know the network mask is the first two FFs.
So the network mask is the first two, and the subnet mask would be all three plus?
Yes. But I know it's an 8-bit subnet.
Because the first two, because of the class.
Right, because they're related, right? Anything in Dearborn, Michigan is going to be in Dearborn. Anything within the subnet, anything in the network, any subnet is going to be inside the network. So if the first two are the network ID, then all three are the subnet ID, then this is the length of the subnet identifier. And so then we are in the 128 subnet. And then a convention is that the .1 goes to the subnet router. That's a convention. It's not followed 100% of the time, but most of the time it's that way.
And you said the subnet ID is all three of them? Like the one?
No,
it's
the
just
network ID in class, and so for any of these problems, we're just gonna focus on class B, because, this can get confusing, and my goal is not to confuse you. It's like binary math. I don't want you to trip up on binary math and lose a bunch of points. That's why as long as you know what a subnet is. So the network ID is the first 2 bytes, and there's only 14 of them that apply to the network ID, so you can only have 2 to the 14th possible network IDs, because the first 2 have to be 10. The subnet ID is the next 8 bits, so it's the 3 put together. So, well, no, I take that back. The subnet ID is that 8 bits. Then the host ID is the last 8 bits. So you have network ID, subnet ID, network ID, total 16 bits, host ID 8 bits, and subnet ID 8 bits. The IP address is then all 3 of those is 32 bits. And the IP address then is an address for a host. And the segments of the IP address are the identifiers. And when you put the identifiers together, you get an IP address. Everybody good with that?
You said the IP address is 32 bits?
For IP version 4. Correct.
Okay.
So we have 16 for the network ID, 8 for the subnet, and 8 for the host.
Okay.
I adopted those for the exam. You have more options than that.
Yeah.
But to keep the exam simple, we're gonna keep it at 16, 8, and 8. That way nobody has to do binary math. Because if we made something at 4 and 12, then you're gonna have to convert it to binary. You know, if I would say like, we'll determine the IP address for something or other, then if it were not on an octet boundary, you'd have to convert it to binary. And that's just not productive, right? We assume everybody here understands binary, and we want to focus on the concept, not on tedious error-prone things like doing binary math. But the caveat is there are other options. But for the sake of the exam, we're going to assume an 8-bit subnet and a Class B network.
Okay.
Yes.
For the subnet, but there's 2 to the 8 minus 3, right?
For the hosts,
For the subnet, because,
for the subnet, well, you can't use the 0,
yeah.
and you can't use FF.
Can you use 1 or no?
That by convention would be reserved for the interior router, or the, I'm sorry, the exterior router. That would be the main router coming into your system.
Good.
That's not a law of physics. But I'm not gonna, that's a dicey question. I'm not gonna ask you that kind of a question. I mean, if I'm gonna say how many hosts you can support, it's, I would say a couple less than 255 would be good enough. Don't try to dissect that, because there are other conventions, like, well, it's possible that you could have 2 subnet routers for a subnet in some weird configurations. And then what you do. So I'm not gonna get into all that. You can't use the broadcast, you can't use the identifier, and there are a couple of others that are reserved for different reasons, right? But I'm not gonna split hairs like that. So I won't even ask the question you pose, I wouldn't ask. But just know generally you have 2 to the 14th network IDs in Class B, you have 2 to the 8th subnet IDs, and you have 2 to the 8 host IDs minus a couple in each, minus a couple in the subnet field and minus a couple in the host field. All right? So any questions on that? Do we want to take a break? I need to get a drink of water. I'm running out of, my throat's getting dry. So we'll take a short break and we'll wrap this up and talk about everybody's favorite subject, routing.